The other method to solve the system of equations is that of method of reduction. And in this case, what you do is you convert this matrix A into either the upper triangular matrix or the lower triangular matrix. So I'll convert this into an upper triangular matrix. So remember the fact that if we want a matrix to be upper triangular, its lower triangle should have zeros. So the entries below the diagonal should all be zeros. Yeah, even before doing that, what you make sure is your first entry is a non-zero, and in this case it's non-zero, of course, so we can ignore that part. But if this were zero, what I would do is I would do some row transformations such that this entry would become non-zero. So if I would in fact interchange one of the rows with the first row so as to make this entry non-zero. But here, since it's already non-zero, I can use this as is. So I can now worry about these three entries to be zero. I'll start with this entry. This entry is -1. For it to make it into a zero, what I can do is I have to add a 1, right? So I have a -1. I'll write it over here. I need a 1 somehow. I need a 1 add a 1 somehow, and I can't just add a constant. That's not a row transformation. I can instead add scalar multiple of a row. So if I were to add 1, 1 is nothing but my half of 2, right? So if I just add half of 2, half of 2 rather, this will become a 0. So what I have actually done is to represent this as a row transformation. I am starting with my second row. So I am starting with my second row, and I am adding half of my first row. So I am adding half of my first row. So this is the row transformation that you need to do to make this entry 0, because remember that our ultimate goal is to make this into a upper triangular matrix. So I want these three entries to be 0. So I'll do this transformation, and you have to remember the fact that you have to do this on both sides, because only then the equality is maintained. So I'll do it over here. Since we are just changing the second row, the first and third row remain intact. So I can copy them as they are. I'll do it for both sides. So I'm changing the second row. I'm adding half of the first row. So -1 plus half of 2. That's -1 plus 1. That's 0. That was the whole point of doing this row transformation, so that this entry becomes 0. Next, I need to worry about this entry. So -1 plus half of 3. So -1 plus 3 halves. That's -1 plus 3 halves. Let's do this carefully. This is negative 1 half, I guess, because this is -2 halves. -2 halves plus 3 halves, that's actually positive 1 half. So this is 1 by 2. Just be careful with your arithmetic. Next, I talk about this entry 1 plus -3 times half. So that is as good as I'll do it here. 1, that's -3 halves. So that is negative half. And finally, if I do it on the right hand side, I have a 5 plus 17 halves. Now that's a bit interesting. 5 plus 17 halves. So that's 10 plus 17, that's 27 halves. So I can write it as 27 halves. So we are good to go now, and the next entry that I want to make 0 is this entry. This entry is currently 1. So if I were to subtract 1 from it, this would become 0. So the way I can get a 1, I can subtract a 1 is if I subtract half of my first row. So now disregarding this. So if I start with my third row and subtract half of my first row, that will, I think, make this entry 0. So let's see if that is actually the case. So again, I'm changing the third row, so I keep the first two rows intact. So I have the third row entry here as 1. So 1 minus half of 2, that's 1 minus 1 is 0. Yes, I got a 0, that was our ultimate goal. Next, I have a 0 minus half of 3, so that's negative 3 halves. And then I have a negative 1 minus negative 3 halves. Let me do it very here. Negative 1 minus 3 halves, minus half of negative 3 is as good as a positive 3 halves. So this is a half. This is a half. Just need to be careful with your arithmetic. And finally, I have on the right hand side, I have a negative 19 minus a half of 17, 17 halves. So this is, let me do this very carefully. Negative 19 is negative 38 halves, and I have a negative 17 half. So negative 38 minus 17 is negative 55, I guess, by 2. So this gives you a negative 55 by 2. Just hope that's correct. So yeah, we have got this entry as 0, and the final entry that I want to be 0 is this entry. So this is already a negative 3 halves. I can simplify this, in fact, by getting rid of the halves. One way to do this is to multiply the second row and the third row with 2, right? Because if I multiply this with 2, even these halves will get cancelled. So let's do that. Let's do two transformations at a time. This is kind of a shortcut. I'm sorry. Sorry about that. So what I need to do is I need to convert the second row to 2 times the second row, and the third row to 2 times the third row, and I'm just do it over here. So I have my first row intact. I'll have a 2 3 minus 3, and 17 over here, and I just need to multiply the second row with 2. So this becomes a 0. 0 multiplied by 2 is 0. Half multiplied by 2 is just 1. Negative half multiplied by 2 is negative 1. And 27 halves multiplied by 2 is 27. Next, 0 multiplied by 2 is 0. Negative 3 halves multiplied by 2 is negative 3. And half multiplied by 2 is half, 1, I guess. Next, I have a negative 55 halves multiplied by 2 is negative 55. So this looks a bit easy to do, I guess, because dealing with fractions is difficult. Let's agree on that. And now I can worry about getting rid of this entry. So what I can do is I can, one way to do this is to add the first entry to the first row entry to this, but the problem in that is then this will become a 2. So I can't use the first row. Instead, I can use the second row. What I can do is I can add 3 copies of the second row. So I need to change the third row to the third row and add 3 copies of the second row to it. So what I am left with is I don't touch my first and second row. They are as is. 2, 3 minus 3, 0, 1 minus 1. I don't touch the first and the second row. So 17 and 27 as is. And now if I have a 0 plus 3 times 0, that's 0. Negative 3 plus 3 times 1, so that's negative 3 plus 3, which is 0. That was the whole point. And then I have a 1 plus 3 times negative 1. So that's 1 minus 3, that's negative 2. And here I have a negative 55, I'll do it over here, plus 3 times 27. Now 3 times 27 is 81, I guess, and 81 minus 55. Let's do this very carefully. 81 minus 50 is 31, I guess, and minus more 5s is 26. So we are left with a 26 over here. And what we have achieved is we have converted the left hand side matrix, the A matrix, into an upper triangular matrix, because all the entries below the diagonal are 0 here. So now I can go back to my equations. If I were to convert this representation to equations, you will realize something interesting happens. Let's do it term by term. Let's do it the first one at a time, the first entry at a time. So 2x plus 3y minus 3z. This is my first entry. Next, you will realize that 0 times x is just 0, so I need not even write that. So, and next is 1 times y, that's y. Negative 1 times z is a negative z, so that's y minus z. And in the last one, it's very interesting. 0 times x is 0. 0 times y is also 0, so I need not write those two entries. So I just am left with minus 2z. And on the right hand side, I have my constants 17, 27, and 26. So if I were to equate this, I would say that all the entries are equal, corresponding entries are equal. So I would say that 2x plus 3y minus 3z is equals to 17. Y minus z is equals to 27. And minus 2z is equals to 26. Now you'll realize why this method is called the method of reduction, because we started with something complicated. We started with three equations in three variables, and we have ended up in three equations. But you'll realize that the last equation is just one variable. It involves just one variable, and so it involves just one variable. You can solve for that variable. If I were to divide both sides by -2, I would be left with z is equals to minus 13. And yeah, this is actually the solution that we got with the previous method as well. But let's go with this. If you have z is equals to minus 13, you can use this with the previous equation, because the previous equation involves just two variables, y and z. So if I were to substitute this negative 13 over here, this would become a y minus negative 13, or rather y plus 13, which is equals to 27, right? And this again is a just one equation in one variable, so you can solve for that variable y, which is just 27 minus 13 is 14. So now you have two variables. So you got one variable and you use that information to find the other variable. And now I can use these two pieces of information to find my third variable using the first equation. So if I substitute these values of z and y in the first equation, what I'm left with is, I'll write it over here, 2x plus 3 times, now y is 14, so I can write a 14 over here, minus 3 times z is negative 13, so z is negative 13 is equals to 17. And let's do this very quickly. So this is negative 3 times negative 13, that's as good as a positive 3 times positive 13. And yeah, if you feel inspired, just solve for x and you'll get the ultimate solution. I'll do it in a jiffy. This is 3 times 14 plus 3 times 13, so that I can get rid of and write as 3 times 27, and I know 3 times 27 is 81. So this is nothing but 2x plus 81 is equals to 17, or if I were to write it over here, 2x is equals to 17 minus 81. Now 81 minus 7 is 73, I guess, so 74, and minus a 10 is 64, so this would be a negative 64. And finally x gives you a negative 32. So this gives you the final value of the variables. And you can check that these are the values that we got from the previous method as well, and these are actually the solutions of the system of equations. You can put these values and check for the equality. So yeah, this is the method of reduction. What you do is you start with your coefficient matrix, your variable matrix, and your right hand side matrix, and you do elementary transformations to convert your coefficient matrix into the either the upper triangular matrix or the lower triangular matrix. I always prefer the upper triangular matrix, so as to get a reduced form of the linear equations, and then you can solve for one of the variables and use that information to find another variable, and use again that information to find the leftover variable. So yeah, this is the way to find the solution to a system of equations using the method of reduction.